When I was asked to talk about Earth's dynamics and its future, I thought about what exactly to target this on because this is a fairly large scope. And so the approach I decided on taking for this particular talk is more or less wrapped up in here. Here's how my talk is going to progress. I thought I would introduce a little bit of the state of play of geodynamics at the moment, what have been the sort of active developments in our domain that have really sort of changed the game for people at this point. Then I wanted to introduce three frontiers of the science at the moment. Now, this is completely opinionated. And, I'm fully aware that there are things outside this scope, but I think these are general enough large-scale problems that they encompass a lot of broad areas of research and activity at the moment. I want to then talk about the approaches we're taking to address these problems in geodynamics and the way in which the field is moving or might be moving. And then I wanted to try and wrap it up with what's effectively a gap analysis. So looking at the outcomes we're wanting to pursue and identifying what are the primary knowledge gaps in getting there. And this is ambitious. I'm not going to come up with a roadmap in and of today by myself, but I like to point the way to it anyway, and what sort of activities have started that may provide a bit of a roadmap into the future. So those of you who are fans of The Big Lebowski, bear in mind this is very much my take on the field as well. Okay, so the state of the field as it is at the moment. So geodynamics in particular numerical geodynamics, has really had a renaissance, I think, probably in the last 10 to 15 years, largely born out of huge ramp-ups in supercomputing power. And this has enabled us to run more and more sophisticated large-scale 3D models, really as a matter of course, to implement very, very complex dynamic rheologies into these systems and start building up what are effectively some of the most highest fidelity simulations that the community has really seen probably in the last 10 years or so. Now, complementing that advancement, we've been seeing real leaps and bounds in high pressure mineral physics. So partly this has come from ongoing experimental work, and that's particularly challenging. But one of the new factors really taking play here is molecular dynamics ab initio simulations, which have been complementing the experimental approaches and giving us a new way to constrain properties such as the viscosity of minerals under high pressure, things that are very, very challenging to do in experimental apparatus in the laboratory, particularly under their extremely low strain that we expect for the lower mantle. Always, chugging along in the background is our understanding of the structure of the Earth from detailed seismology. And I think, 20 years ago, there was sort of just an explosion of 3D models for the Earth's interior, and these have become more and more refined as we've moved on, to the point now where we're able to inform and test a lot of the physical dynamics of what's going on by comparing to the seismology picture of the Earth that we see today. And lastly, a lot of our knowledge of the deep Earth comes, originally from cosmochemical models of the Earth. So what we expect the Earth to be like cosmochemically, assuming a certain chondritic composition, and then looking at the Earth itself and understanding where the variations exist and what to anticipate. But more and more, this is becoming supplemented by additional measurements from things such as geoneutrino constraints, which, for instance, can give us concentrations, at least on some of the major heat-producing elements like thorium and uranium in the deep interior, their distribution, and then it allows us to compare at least, those particular nuclides to cosmochemical results and understand a little bit more about the substance that the Earth was originally created from. So let me really kick off, with that being the state of play and where the big advances are. These are the frontiers, I think, of knowledge for the earth sciences as they stand at this point. And I'm going to kick off, and this was talked about a little earlier, with the deep past. So over 10, probably 15 years ago now, the NSF commissioned a document on the big problems in earth sciences. And it was a great document with 10 outstanding problems. Two of those problems I'm really revisiting here because I still think they're some of the most fundamental problems facing our field at the moment. So the reason why Earth's history, and in particular the deep past, is of particular significance for geodynamics is that somewhere buried, around 3 billion years ago, plus or minus 2 billion years, depending on whose paper you read, plate tectonics originated. So this really is the paradigm for the dynamics of the Earth today. It's how we understand the Earth. And yet there was a period of time when the Earth probably behaved very, very differently. It's probably quite volcanically active. It may not have had significant horizontal motions in tectonics like we associate with plate tectonics today. So that transition from whatever the pre-plate tectonic regime was into plate tectonics is one of the most fundamental changes in geodynamics. And it also set the stage for a subsequent evolution into the habitable planet we know today. That then ties I think, to the evolution of the atmosphere and thus the effect of geodynamics on the evolution of life. These things are connected to tectonics. The atmosphere is directly connected via volcanic degassing. So these days, volcanic degassing via the mid-ocean ridge system is one of the major inputs of greenhouse gas, CO2, to a lesser extent methane, into the atmosphere. And over time, that volcanic input was expected to be much, much greater on the early Earth. Coupled to that, though, of course, plate tectonics creates the topography we see. It enables CO2 drawdown by the erosion of mountains and the CO2 silicate cycle, and subduction also provides a mechanism to recycle. So this really, ties, I think, the connection between the evolution of the atmosphere, the evolution of surface conditions, and thus the conditions for life with the large-scale tectonics of a planet over long time periods. I won't go into it too much here, but we also have the case that the core and the geodynamo are still not very well understood. I think there are big uncertainties in the core's thermal evolution, mechanisms for internal heat production, even to the point of estimates for the inner core's age, whether or not it came into existence 500 million years ago or 1.5 billion years ago. It's not particularly tightly constrained yet at this point. Now, coupled then to those questions of what was going on at the surface, the continents at some point formed. They may have existed in some form earlier on, but certainly not like modern continents. And that continental aerial extent grew through time. But coupled with that, of course, is the exposed continental aerial extent, the amount of continental material that poked up above the sea line. And that has been suggested for a long time, and I'm thinking back to Kampenbali's original paper here, that increased significantly sometime in the Precambrian, maybe moving into the Proterozoic. And this would have had a dramatic effect then on the availability of nutrients via erosion into the ecosystem and thus on the evolution of life as well. I mentioned a little earlier the significance of volcanism earlier on, but this is to the point where we're actually talking almost about a very, very different tectonic regime. Volcanic heat transport is extremely significant on a hot early Earth, to the point where it completely gives us conductive heat transport through the lithosphere as a transport mechanism. So when we're talking about in a situation where volcanism is carrying more heat than any other mechanism, it's often been called a heat planet. In the older literature, you may hear it referred to as a mantle plume-like regime. But this has been suggested to have operated in the early Earth, particularly in the absence of something like plate tectonics to lose the heat. And lastly, we have impact bombardment. If we look at the face of any planet, as was shown in the previous talk, impact bombardment is extremely important in the early evolution of the solar system. And it's also a reasonably important geodynamic driver as well. It can drive geodynamic behavior in the early Earth, which is what I'm showing in this figure here, where a large 300-kilometer impactor here has driven subduction in a Hadean-type mantle model. So the wrap up for this for us, though, is that the evolution of modern tectonics and even the state of the planet today, you can't really understand it unless you have this context from the past history of the Earth. And that, I think, is the reason why this question of the deep past, and in particular the geodynamics of the deep past, is still so critical and, still really unresolved. The second frontier I wanted to talk about is sort of the deep past. We're now into the deep Earth. And I focused in particular just on the lower mantle here, and, just in the interest of time, but one could, have just as many slides on the core or even, the upper mantle rheology as well. But suffice to say for us that the lower mantle is still poorly constrained. What we do know is that it's a mixture largely of bridgemanite, with secondary ferropericlase magnesio-wolstite. And then we have other minor phases like perhaps aluminium and calcium perovskite down there as well. Now, the proportions of those aren't well defined. We don't have really tight chemical models that give us a canonical value for what these mineral proportions are at different parts in the lower mantle. But this is also, quite challenging because this means our rheology potentially can vary quite widely. So the viscosity of these minerals individually has been difficult to obtain experimentally, just simply because the pressure temperature constraints are high. And we have very, very low anticipated strain rates in the lower mantle as well, which means they're challenging experiments to do. In the recent years, we've seen a lot of ab initio molecular dynamics calculations, both from D double prime to perovskite structure minerals, that have started to shed light on a lot of the behavior of this lower mantle material. But I think what's really missing and what's needed is a way of going from these individual mineral properties up to bulk properties of an admixture of these minerals. So we're talking about mixing models here. And these in particular, there's a few in the literature, but under the conditions for the lower mantle and the viscosity contrast we expect, bridgemanite's on the order of 1,000 times more viscous than ferropericlase. So under these sort of conditions, those sort of mixing models aren't well developed or well constrained experimentally, I guess you'd say. And add into that mix, then we have complexities such as the iron spin transition at about 1,000 kilometers. So iron and ferropericlase, its D shell electrons go through a transition to a high to low spin state at about this time. This has an impact on seismic wave velocities. It has an impact on the rheology of these materials as well. But in a complicated way, because it depends on the distribution of the minerals hosting the iron in the first place. Add into that, on the bottom of the mantle, we have the D double prime layer, which acts both as the thermal boundary layer to the core, so there's extremely large temperature contrast above it. But as we heard earlier, we have the LLSVP structures down the bottom. We have ultra low velocity zone structures way down on the core mantle boundary itself. And then we have a phase change, a high pressure phase change for the cooler material at least, into a post-perovskite phase at the core mantle boundary as well, which is anticipated to have a lower viscosity than bridgemanite and thus a very different behavior down there as well. So this is an enormous amount of complexity happening in the lower mantle. I think that we're really just starting to get a clearer picture of in the last 10 years or so. But it also means that it's a highly complicated system, which is really, really relevant for us to know about. It is the biggest geochemical reservoir, accessible reservoir on the planet. And thus, as a result, it's really important to understand the dynamics of this region as well, which feeds into things like our Earth evolution models and understanding how the lower mantle has evolved over deep geological time. Now, the third frontier I wanted to talk about is, of course, the final one. Final frontier being looking out into space. So I've put in the background there the James Webb Space Telescope first deep space image. So you can see all those billions of galaxies around in the background. But of course, estimates suggest that, on average, most stars have planetary systems. So even within our galaxy, we're talking about potentially billions of planets. Now, only if I guess almost a minor number of those have representatives in the solar system. By far, some of the most common planets identified in the exoplanet catalogues are things like hot Jupiters, so gas giants extremely close into their host star, which don't have any parallels in our solar system. Super Earths, so terrestrial planets larger than Earth, are extremely common. We have no representatives of those in our solar system. So already we know, looking out in the exoplanet catalogue, that what we're going to expect from planets out there are going to be representatively quite different from what we see and to some degree have been trying to understand in the solar system. So that's just from the gross physical characteristics. From the chemistry, it's even worse because these planets are going to have inherited a very different cosmic chemistry. They're forming in stellar nurseries that are going to have vastly different bulk elements, compositions, than the solar system in particular did. They're going to have different radiogenic nuclides, so different proportions of heat production. Earth inherits, and the solar system inherited a number of generations of radionuclides from dying stars, as summarized by Lugero in her paper. But there's no reason to expect any other planet inherited those in similar proportions. So most exoplanets we expect to have quite distinctive and unique radiogenic nuclide compositions. They're going to have very different planetary formation pathways. Planets migrate during formation. The solar system seems to have been a bit of a bit of an unusual case in that Jupiter and Saturn somehow interacted to prevent gas giant migration in the solar system, at least for too far. So the solar systems themselves are going to have very different histories and very different final structures on average than our solar system. Coupled to this, we have on an individual planet scale. So for a given terrestrial planet in the exoplanet catalogue, we'd expect different heat budgets. We'd expect fairly different mineral assemblages then. I mean, olivines everywhere in the universe, true, but the proportions of minerals within a given mantle are not going to be necessarily Earth-like at all. And that means they're going to have different rheologies. They're going to inherit different volatile budgets. And this is important not just for rheology again, but also for things like the ocean volume, perhaps even ocean compositions, what it's made of, ocean-continent ratios, and thus things like nutrient flux into the oceans. These are all going to be different. Now, these factors are all really critical, or have been postulated to be critical, for the evolution of life on Earth. And if you play with these parameters, then you could expect quite different evolutionary outcomes. So, and plausibly, I mean, even for very Earth-like planets with different physical sizes, you could expect quite different behaviors, and point to a couple of references there that started off a bit of debate about this. But I think, interestingly, we're coming into a period where we're going to be able to just apply constraints to these. We're not going to need to wave our hands about what's possible and what not. I mean, this is from the James Webb Space Telescope, and it's actually identifying water in the near-infrared spectra of a hot gas giant near its star. But the fact is we're analyzing planetary compositions now. From the technology available to us, we're looking at their atmospheres, we're understanding their constituents. The field only moves forward from here, and I think in the long term, our ability to model planetary atmospheres is going to be an extremely important diagnostic on their behavior. Now, the task ahead of us, I think, in geodynamics is huge. I mean, we have trouble modeling the Earth in its full complexity, let alone other planets with different mineral compositions and assemblages with different internal heat production. And I guess a broader question is, if we step back, well, how exactly do we go about modeling this degree of complexity? The possibilities of models you could run are, definitely endless. What do we do? What's our approach? Now, generally in geodynamics, and this is probably more general in science in overall, Is that there are really two approaches to the problem. One is a reductionist style approach, where you consider the elements in a particular problem. So it might be the physical properties of a given mineral. And then you code those particular properties into, say, a simple geodynamic model, and you look at the difference from, your simple model to perhaps a constrained model, like control. Now, this is all well and good, and you can understand the effect of simple variations quite well. You can develop a very good qualitative understanding of what's happening in this system. But of course, the risk of breaking things down and looking at only individual components is that these components generally compete in geodynamic interiors of planets. And so you run the risk of leaving out competing factors that may alter the way in which individual components have relative importance. So a different approach then is just to throw everything in. So this is the complex systems approach, where you would basically code in as much of this complexity as necessary, and you treat the dynamics of the system then as an emergent phenomenon. Whether or not you get something like the geodynamics of Earth is somewhat irrelevant. This process is emerging then out of the complexity of the small scale processes you're considering. Now, the nice thing about this is that you're able to include a diversity of mechanisms, a diversity of ways in which small grains of bridgemanite might be creeping in the lower mantle, be it dislocation, diffusion, pearls, pure climb. We can include all these processes in and look at the way in which they interact to give you broad-scale geodynamic behavior. So this allows you then to look at emergent properties of this system, so such as looking at the way in which tectonics comes out of this complexity. And it also allows you then to start identifying which parameters or processes are of primary importance, a high priority, and which ones have a much lesser effect. Now, the risk, of course, in a complex systems approach is the system can rapidly become extremely complex and thus difficult to deconstruct and understand. And this is where advances in things like machine learning and classification algorithms come to play a part in actually understanding what's going on in a sufficiently complex system. So I think one of the approaches that geodynamics has taken in the past is to make sure we benchmark the emergent behavior we see in our models against relative constraints that we get, for instance, from the Earth in particular, but also, more generally from planetary information that we can glean remotely. So to give you an example, earlier on, a lot of our understanding of Earth's thermal evolution we took from constraints on heat flow today. We looked at variations in heat production, and we constructed thermal evolution models to understand the broad scale energy budget of the planet. When we run more dynamic models, people were looking in particular at plate motions, so the variation in plate motions, the mobility, the localization of deformation as proxies for modeling Earth-like behavior. And then if you looked at these systems over time, you may bring in different geological constraints to these systems, somewhat summarized in these papers here. At a global scale, and in 3D in particular, we're able to run models now in 3D that can emulate global seismology, so we can try and understand where the structure of the Earth that we see from seismology came from a dynamic point of view. And we also include information such as, the geoid for the Earth, which can constrain the viscosity profile of the Earth, but other large-scale physical measurements we can make of length of day, moment of inertia, all of which are related to the internal structure of the planet. Now, as a really brief example, I just wanted to do this one, which is Venus, because something I've worked on recently, which has often been considered to be Earth's twin. From the old Venera missions, the samples that were analyzed there, to their level of precision, did suggest that the surface of Venus had affinities with terrestrial rocks. And so there's been an assumption there that Venus largely is Earth-like. And that we can use Earth-style rheologies to understand it, albeit perhaps without so much water. But of course, Venus is halfway towards Mercury as well, and Mercury is quite cosmochemically unusual. And so I just wanted to flag, some of the recent results we have from Venus from, in this case, an update of Venus's moment of inertia. But first, to set the scene, I guess, as we all probably know, Venus doesn't have a detectable magnetic field. It has a slow retrograde rotation, which probably plays a part, but the lack of the field has been largely suggested to be due to the fact that Venus, it has no inner core. And this actually has profound implications for Venus. If it has no inner core, then it means the planet has been cooling slowly, slowly enough so that that inner core hasn't been able to crystallize, which for most thermal evolution implies that it's had no plate tectonics for any significant portion of its history. So this is a fairly important parameter to understand for Venus. Now, the issue with Venus is it spins so slowly that it's very difficult to get an idea of its moment of inertia. But using recent radio-derived day calculations, Margot came up with a new estimate for Venus's moment of inertia. And then what we did was then take existing mineral physics models from a community code and library, Burnman, to assess the possible end members we could expect that fit this new moment of inertia. So we actually ran a bunch of models, and I just parameterized two of the end members we have here. The blue line here in the first panel is for a pure iron core, something that fits the Earth's structure reasonably well. And, if we converge to fit the moment of inertia, we end up with an iron core with a radius somewhere over 3,000 kilometers or so. But the other alternative is we do have the possibility of putting a lot of light elements in Venus's core and seeing if they fit. And if you do that, in order to fit Venus's mass and moment of inertia, you actually need an extraordinarily large core, about 4,500 kilometers in radius. And this also implies then to match the moment of inertia, you actually have a very dense inner core over 2,000 kilometers radius as well. These are very, very profoundly different systems. This is just plots then of the pressure, the internal gravity, and also the temperature you'd expect, both for an Earth-like composition, an iron core, and for an iron silicon core, so significant light elements in the core. So at the ends, there is no distinct way with something as simple as just moment of inertia to tell these two end members apart. They have the same prediction, but they are quite vastly different, which, again, belabors the point of integrated constraints. We need additional cosmochemical information on Venus to be able to tell these apart. And thus, we really need samples from Venus, either via a mission to the surface or somehow returning samples from the surface to be able to really analyze Venus and understand its cosmochemistry better, whether it really is a twin of the Earth cosmochemically or whether it has affinities to Venus, to Mercury rather. Now, with regards to the Earth itself and what we can say about it recently, we have the ability to probe the Earth, and I'm not going to belabor these points because they're going to be focused on in upcoming talks. But I just wanted to raise the flag for a few areas where there's been significant leaps, and these include cosmic chemistry. We've had significant improvements in our understanding of the heat flow and the thermal budget of the Earth, and this includes from recent constraints from geoneutrinos, which are giving us a picture, an independent picture of the internal elemental structure, at least with regards to those heat-producing elements. We have, just ongoing massive refinements in global seismology, which are giving us a hugely clearer picture of what's happening, particularly within the deepermost portions of the mantle. And we're also complementing this with advances in high-pressure mineral physics, both from the experimental results and more frequently from the ab initio molecular dynamics calculations that are being undertaken on high-pressure phases. So I'm not going to go into these, but I thought I'd just flag that there is still significant work required to bridge these scales. To go from mineral scales up to global seismology and then be able to inform geodynamic models. These are not trivial acts. And I think, bridging those scales is still something that's going to underpin utilizing these advances in improvements in geodynamic models for the future. To come back then to other worlds, I've raised the point of planetary geochemistry previously and how it's related to the stellar chemistry. Now, stellar chemistry is something we can constrain. There's enormous libraries of photochemistries of stars. But of course, for the solar system, there's not a one-to-one correlation between the elemental spectra of the sun and the planets. There's a huge variation during the process of planetary formation in those elemental compositions. Not least, you lose most of the hydrogen and helium, but you have significant volatile loss during planetary formation and fractionation of a large proportion of the elements. Now, this is by no means a resolved problem. It certainly varies significantly within the solar system between the terrestrial bodies and the asteroid population. And so what we actually see within the solar system is we see large variations in bulk mineral composition, even for, very similar terrestrial bodies, Mars, the Earth being a classic example. There is bulk mineral composition variations between the mantle of Mars and the mantle of Earth. And this is even more so when we compare it to asteroidal populations as well. Now, a predictive framework for saying, we're forming a solar system like this, and here's the final composition these planets are going to have, and here's the minerals they're going to have, that doesn't exist yet. We're not at that stage. So there's significant refinement in understanding the partitioning of elements into planets via that planetary formation process that still needs to be improved upon. And then even from an exoplanetary catalog, we'd expect even more chemical variation than what's observed in the solar system. Huge variations in redox. We could have, all sorts of exotic variations in what we see in terms of their composition, from extremely reduced to more oxidized, such as the Earth. We're only just starting to have a sort of primitive understanding of the potential mineralogical variations that implies. But, I think it's fair to say that the spectrum of potential interiors of planets is largely unknown. It hasn't been systematically studied at this point. And again, just to bring it back then, if we're thinking about exoplanets, what sort of ways could we benchmark them? It's not the case that we have a geological record we can turn to understand these behaviors and be able to try and model the planetary interior and compare it back to the same suite of observations we use on the Earth. So the ways in which you can potentially constrain what an exoplanet is doing, at least from a geodynamic point of view, the obvious low-hanging fruit is then its atmospheric composition. There is a relationship between the geodynamics and the volcanism, and also with, via volcanism to the degassing you get on a planet, so the volatile release and atmospheric replenishment, but then also to the recycling via subduction and erosion of mountains. So these things are tightly constrained, and you can imagine, running complicated 3D models with an atmospheric model on top of it and making predictions about how that atmosphere evolves. Now, of course, you do have the complexity then of geomicrobiology and the way in which it modifies Earth's atmosphere, and this is an important consideration, but also an important opportunity in that if you understand the parameters giving rise to planetary atmospheres abiologically, variations to it then raise the possibility of biological activity, which would be really, really nice to be able to tie down. But I don't think our models are at a stage where we could be diagnostic about that yet. In fact, we're not at a stage where we have an agreement on what is a diagnostic atmospheric signal of plate tectonics. And I think largely this needs, an improvement in the coupling of geodynamics to volcanic, to degassing, to atmosphere models. And it's just something that hasn't been worked through, I think, in enough detail yet. So we could also foresee, we could use things like the geoid, the gravity, size of the planets, the moment of inertia. These things can constrain the interior of a planet. They can give us a trade-off between your internal temperatures and internal compositions and feed into information about that and allow us to make predictions for geodynamic models. And then I just throw this last point in as, perhaps I'm being a bit over-optimistic here and a bit cheeky, but in 2004, during the Sumatran earthquake, That quake and the mass change associated with it, as part of the oceanic lithosphere went into the mantle by about 10 meters in places, changed the length of day of the entire planet by 2.68 microseconds. That's reasonably difficult to discern from satellite observations today, but it's there. It also shifted the pole, though, by about 2.5 centimeters. So there's a rotational effect on the Earth. Now, this is hard, but it's not impossible to detect that sort of pole change remotely from rotation. So technically extremely challenging, but not impossible. And it does raise the possibility that if we had that level of precision in planetary modeling, monitoring of other planets, there is a chance that we could, basically derive unambiguously whether or not it had ongoing active tectonics or something like subduction. Right, so to sum this up, the state of the field as we are. So I think, the one thing we've seen in the last 20 years is huge advances in the computational power available to geodynamic modeling. And in the approaches we use, they're becoming more and more sophisticated. And we're also able to build greater fidelity into these models by using results from our increased understanding of high pressure mineral physics. The critical frontiers, at least the fun ones I like anyway, are really exist in understanding deep time, the evolution of the planet, understanding deep planetary interiors, which we're still in our infancy on, particularly beyond Earth structure, and then understanding exoplanetary tectonics as a spectrum of possible, mineral behaviors for generalized silicate compositions. What we really need, and I've tried to highlight a few gaps along the way here, but this is no means a formal gap analysis. But I think, in order to address those sort of big frontier style problems, it's worthwhile as a community to have that sort of process to undergo a gap analysis and then plot a roadmap forward. What do we need as a community to make this happen, to move the work forward? And I just wanted to flag that there are a number of initiatives that are doing the right things, already underway. There are some great examples of community codes, groups working together, and I put in the CIG suite there as a link. And there's also work towards providing community rheological models as well. From a mineral physics point of view, Burnman's an example, but from a complex rheology point of view, it would be nice to see these archived and to be able to draw on them more generally. I think computational resources are always going to be one of those things that's quite competitive. There's a number of tiers of access. There's probably not, I think, as an international community, any sort of consensus or generalized way to providing this to the community as a whole, although I know nationally there's a number of independent initiatives. And then lastly, agreement and I guess the provision of observational tests and data archives. And I note again that a lot of these exist to varying forms, for Earth's observations and gravity models, to geoid models for other planets, to planetary data archived from NASA. There are archives with this data available in different formats, but it would be good to see an archive specific to geodynamics and the testing of geodynamic end members. But look, I think, steps are being made in all of these directions. There's a lot of good stuff underway. And I hope in the future we see, these fall under the umbrella of a roadmap taking geodynamics forward, I think, into the next 10, 20 years to address some of these big problems that I've talked about today. All right, that's the end of my speech. Thank you very much.